Hello grade 12s. In this next video, which is part 2 to our equilibrium lesson, we're going to solve these two problems. Okay, going to get right into it so I can make this video as short as possible. I've realized that going over both questions, both examples, probably going to take a bit too long for one video, so I will divide it even further into two other videos. Our first video right now will be on solving question 1, and our next video will be solving question 2. Okay, now before we get into actually solving this, I don't want to get straight into it, but I do need to say what an ICE table is. Now, the reason I have a picture of this actor here, if you know who this is, you'll know why I have this picture here. A method to solve these sorts of problems that really helps is to use what's called an ICE table. So this is Ice-T, famous actor. Maybe you might be too young to know him, but I thought he has to be here because we're going to be talking about ice tables. Another thing I have that way, if we were in class, I would have playing most every day would be the class anthem, which is Vanilla Ice's "Ice Ice Baby." I'll post a link to that song, to that video on YouTube on our team's website, on our team's class site. Okay, but ICE stands for our initial concentrations or mole values given to you in the question. C stands for change, how much those values, mole values or concentration values, will change. And E stands for equilibrium. Okay, our equilibrium values or expressions. Now let's get back into it. Okay, so take out a highlighter. All right, so here we have a sample of xenon tetrafluoride is created by mixing these two reactants, xenon and fluorine gas, at these concentrations respectively. So here are their concentrations. The final amount of fluorine gas at equilibrium, that value is really important. I'm going to change that color here. So fluorine gas at equilibrium has a 2.2 mole per liter concentration. So it's asking us then to determine the equilibrium concentrations of all reactants and products. Okay. As you would in stoichiometry, as you would in grade 11, you always begin with a balanced equation. Okay, now here, usually you've seen arrows in the forward direction, but we know that at a dynamic equilibrium, they proceed in both directions. Okay, so that part might be new. I often won't draw it this way. It's often drawn as two half arrows like this. So you'll see me do it that way. They should be roughly equal. All right. So they're often drawn like that. Okay, so ICE. I-C-E. All right, so from our question here, we have 3.4 big M stands for moles per liter, 4.7 big M moles per liter initially. These are our initial values. And initially, before these two react, we have no product made, right? So we're going to say 0. Now, these values will change. Our reactants will go down. They are being consumed to make products. So if they're going to go down, they're going to change by a negative value. That negative value is going to then also relate to a certain amount. We don't know what that is. We're going to call that x, a certain amount x related to their coefficients. Look how it works. 1 xenon, 1 mole per liter of xenon is going to be consumed for every 2 moles per liter of fluorine gas to produce 1 mole of product. So it'll just change, xenon will change by negative x. Fluorine will change, it will also decrease, so it'll be negative, but it's not going to decrease by 1 mole per liter of x, it'll decrease by negative 2x, again proportional or related to the coefficient in the balanced reaction. Our product is also going to change, but it's going to increase in concentration, so it will have a positive sign. And that positive sign is then also going to change by a certain amount, unknown amount x. We'll call that x related to the coefficient in the balanced equation. In this case, it's just a 1, so it's positive x. Now, what you do with E is you just take I and C and you add them together. I plus C gives you an expression at equilibrium for xenon, an expression at equilibrium for fluorine, and for xenon tetrafluoride, 0 plus x is just x. So now we have expressions for all of our substances here at equilibrium. Now that important piece of information given to us in the question is 2.2 moles per liter of fluorine. We know that at equilibrium, we have a certain concentration, right? That is 2.2 moles per liter of fluorine. And we know that an expression at that equilibrium is right here. It's 4.7 minus 2x. We can equate these two and solve for x. So 2.2 minus 4.7 is negative 2.5 is equal to negative 2x. Divide both sides by negative 2, and we get that x is then equal to 1.25. Okay, 1.25, we know that at equilibrium, our concentration then for xenon tetrafluoride, because x represents a concentration at equilibrium, is going to be exactly that, 1.25 moles per liter. We can now begin to figure out what the concentrations are of the other substances. In this case, though, we know what this concentration is given to us in the question, so really all we have left is xenon. Xenon gas at equilibrium is 3.4 minus x. We know what x is, it's 3.4 then minus 1.25. And what do we get there? We get 2.15. Okay, so now we have concentrations for all of these, all of our reactants and product at equilibrium. Here, here, and here. Now this last part, I don't usually do this in class. Try to save some time for the next class and review as well, but I'll just do it here in this video because you can always pause, right, or review later. But let's finish it off. So we now have all the concentrations at equilibrium. That was the main part of the question. Now this last part, what is a percent yield? Right, what is a percent yield of this reaction? With one product, it's pretty simple. There is a bit of review you might need to do. If you recall from grade 11, the amount of product produced is limited by, of course, your limiting reagent. So you'll need to figure out what that limiting reagent is. In this case, the limiting reagent is fluorine, not xenon, it's fluorine. Right, so fluorine is our limiting reagent. Now, how we figure that out? Well, you have to test it. I can post links to a limiting reagent lesson. Please do ask, although know that this is not the focus. This is definitely not the focus of equilibrium. Okay, but I do want to go over percent yield and show you what it really looks like given an equilibrium problem as opposed to your stoichiometry problems that you are used to from grade 11. Okay, so fluorine and xenon tetrafluoride exist in a 1:2 ratio in this reaction. So we can say, therefore, the concentration of xenon tetrafluoride, according to this mole ratio, then would be 4.7 divided by 2 because it exists in a 1:2 ratio, or 2:1 ratio, reading left to right. So that will give us a value then of 2.35 moles per liter. This is our theoretical amount. Right, this is how much should have been produced stoichiometrically in a 2:1 ratio. But if we're looking at percent yield, right, what we really need to look at is what is a concentration at equilibrium? Well, we know what x is. Right, x is right here. We know it's 1.25 moles per liter. What we theoretically should have had, given the stoichiometry, is 2.35 moles per liter times 100%. And we get an actual percent yield of 53.2%. Given 3 sig figs from the question, sorry, not 3, given 2 sig figs from the question, it should just be 53 here. We can go back now, and now that we're finished this should actually be 2 sig figs, so it should be 2.4. Actually, sorry, this is not the final answer. Do not round numbers, values until we get to the very end. Here, I'm going to make reference to this. So this is then really 2.2, right? Just 2 sig figs. This is given to us in the question, although if we're going to treat it as we should treat the others, it should really be 1.3. Right, so those are our values at sig fig. So our first question is done. Hopefully that made sense. We're going to get into the next question, question or example 2 in our next video.